Welcome to the third talk of this session. I'm very happy to introduce Thomas Lamb from the University of Michigan. He's going to talk about positive configuration space.
Thank you, Sarah. I'd like to thank all the organizers for inviting me to speak. It's great to see everyone. I am a bit sad about, I was planning to visit Mittag-Leffler, and where I've never visited before. I had an opportunity, I recall, when I was a graduate student, and somehow it didn't pan out. And since then, I've managed to miss every chance I've had of visiting. So it's very bad luck for me. So I want to talk about positive configuration space. And this is joint work with Nima, Arkani-Hamed, and Spradlin. The paper we're talking about is on the archive, and this talk is being recorded, I think. Okay, so this the talk is part of subject of total positivity and total non-negativity. Sorry. Okay. Yeah, and so I'll start by talking about two sort of classical, two older objects, and then as an analogy with the space that I'm going to talk about. So the first one is the total non-negative part of GLN. So what's a total non-negative matrix? That's a matrix such that all the minors are non-negative. So this matrix here, if you look at any minor, the determinant of this is 1, which is non-negative. This matrix, actually, all the minors are all the entries. All the minors in particular, all the entries are positive. This is actually a totally positive matrix. So the second space I'll talk about is the total non-negative Grassmannian, and I have this sort of cartoon here. As we go down this list, the spaces sort of become more geometric and less, in some sense, algebraic. So the first object is sort of total non-negative matrices. I really just think about it as a matrix. With the total non-negative Grassmannian, we start getting some sort of matroid geometry, and we tend to think of it a little bit in terms of vector configuration. So here I've drawn a little cartoon of a point in the total non-negative Grassmannian GR26, and I drew a sort of degenerate, sort of a special configuration. The vectors 2 and 3 are parallel, and the vector 4 is the 0 vector. The positivity condition here, so in the first case, the positivity condition is this determinant is positive, and in this vector configuration case, the positivity condition is that the vectors are sort of ordered from left to right. So I put them all on the same side of a hyperplane, and they go from left to right, 1, 2, 3, 4, 5, 6. So the vectors are labeled. And then I'd like to talk about this sort of the technical name is the total non-negative part of the Chow quotient of the Grassmannian. That name is a little bit long, so for short, I'll call it either positive configuration space or non-negative configuration space. Now, and now it's even more geometric, and as far as I know, there's no analog of a matrix to describe points in the space. So this is all three of these things are topological spaces. To describe a point in the first space, I give a matrix. To describe a point in this third space, I've drawn a picture of a point, and the picture of a point is I have 2-point configuration. So this is like the 3-6 case, and what I've drawn is a point configuration in P2 and another point configuration in P2, and they're compatible in some way. And this point configuration is considered up to PGL2, so projective transformations won't change this. Won't change what point in the topological space I'm after, but a point in this topological space is represented by such a picture. Okay, so let me get to some more specifics, and let's start with this the total non-negative part of GLN. So this is a classical case, and these authors here, Schoenberg, Gattmacher, and Krein, Lohner, and Whitney, they worked in the 30s to the 50s. And as I said, the definition of the space is just, we take n by n non-singular matrices, and then you ask that all minors, all submatrices have non-negative determinant. So that's some, a matrix is either satisfies the condition or doesn't. So this is some subspace of GLN, and it acquires a topology from it. There are two things that I want to mention. I mean, there are many theorems about the total non-negative part of GLN, but I want to mention sort of two features, which are sort of why a combinatorialist might care. And I think sort of combinatorialists got into this game mainly because of this second, the second thing that comes up, which is that there's a close relation between planar networks and total non-negativity. It's formulated, so what is this correspondence? So I give you this planar network, and I think of it as I have a bunch of sources, 1, 2, and 3. I haven't drawn the arrows because all the arrows are, all the edges are directed towards the right. So I have some sources 1, 2, and 3, and I have some sinks 1 prime, 2 prime, and 3 prime. And the edges have some weights, which are positive real numbers. And if I don't weight it, then there was a 1. The edge has weight 1. And what I do is I read off from a matrix. And so this entry here, the 1, 1 prime entry, is the weight generating function of paths from source 1 to sink 1 prime. So there are 2 paths from 1 to 1 prime. You can go straight there, or you can go like this. And the weight of this path is just the product of the weights of the edges, which is 1. And the weight of this other path is the product of the weight of the edges, which is AC. So that's this entry here. And so it follows from this Lindstrom-Gensel-Viennot lemma or theorem that this matrix, the resulting matrix, actually all the minors are non-negative. In fact, we know a combinatorial interpretation of all the minors. The minors can't non-intersecting families of paths with particular sources and sinks. And I believe Brenty was the one who observed that every matrix, every total non-negative matrix comes in this way. So there's in some sense a perfect correspondence. So I think this is this network story is where sort of algebraic combinatorialists got really into total non-negativity. Let me mention another thing, because I'm going to talk about, this is a feature of all of the spaces I'm talking about, is that they have a cell decomposition. So the topological space is a disjoint union of subspaces, and these subspaces are homeomorphic to open bores. And usually there's some combinatorics associated to parametrizing the points, and there's a separate kind of combinatorics associated to parametrizing the cells. And in this case, it can basically, from the work of Lohner and Whitney, you can obtain a cell decomposition of this topological space, and it has n factorial squared cells. In fact, if you look at the closure of the cells, you recover sort of double Bruhat order, and I think that's an observation of Lustig. I think was the first who realized that Bruhat order was related to this. Okay, are there any questions?
I see no questions so far.
Okay, so let me go on to the second space, which is the total non-negative part of the Grassmannian. And this was defined by Lustig in 1994 and Postnikov 10 years later. The definition we use is Postnikov's. And what's the Grassmannian? So we have two integers k and n. The Grassmannian parametrizes k-dimensional subspaces of an n-dimensional space. And often we think about it is you take a k by n matrix, and the subspace is the row span of that matrix. And it will have the correct dimension if the k by n matrix is full rank. But of course, this description has the bad thing that many different, there are many bases of a vector space. So there are many different k by n matrices. So you have to mod out by row operations. And the total non-negative part is the subspace consisting of k by n matrices where all the k by k minors are non-negative. So the k by k minor, so the max, so here's a k by n matrix, k is less than n. The maximal minors are the k by k minors, and the k by k minors are indexed by which columns we use. So you pick a collection of columns, and that will give you a minor. So the determinant of that submatrix is the Plücke coordinate, and you insist that they're all non-negative. Okay, so that's a subspace of the Grassmannian, and there's and here's some sort of a snapshot of some of the many things we know about it. So the combinatorics of the cell decomposition. So the cell decomposition was described by Postnikov and by Reach, and sort of Postnikov described like very many different ways to index the cells, and I wrote down here my 3 favorite ways, and I think for today's talk, the only one that's sort of relevant is the matroid point of view, is to index the cells by positroid. So how do we do this? The k by k minors of this k by n matrix, we insist that they're non-negative, but they could be either positive or 0. And if you remember which ones are positive and which ones are 0, then you get a matroid. So and the matroids that come up in this way are called positroids. So that's the definition of positroid, and the positroids were classified by O. Now, so earlier I said that in this previous case, in the case of the sort of n by n matrix case, what came up is Bruhat order. And here, instead of Bruhat order, what we have is we have just containment of matroids. So the cells are indexed by these positroids, and I'm not going to give all the combinatorics associated with positroids, but there's some collection of matroids that are classifying these cells, and one cell is contained in the closure of the other if there's a containment between these matroids, just as a collection of bases. Postnikov has developed a sort of technology to parameterize these cells, and I've drawn a cartoon here of the kind of combinatorial object that comes up called a Playback graph. And I also want to mention a result of mine with Dressian and ACOW, which is that this topological space is homeomorphic to a closed ball. And the way one might think about it is, in some ways, it's quite like this topological space is quite like a polytope, and we have some nice combinatorics indexing the faces, and the topology agrees with the combinatorics. Okay, so let me go about defining this total non-negative part of the Chow quotient of the Grassmannian. So first, what is a Chow quotient? I'm going to take the point of view of the Grassmannian to start. There's a few ways to think about this space. So inside the Grassmannian are the collection of points which are as generic as possible. So those are the ones whose matroid is uniform. In other words, these are k by n matrices where every k by k minor is non-vanishing. So I call this the uniform matroid stratum. And there's there's an action of GLN on the Grassmannian acting on the ambient n-dimensional space. So the Grassmannian classifies the subspaces. If I take a linear transformation of the ambient space, it will take a subspace to another subspace. If that linear transformation is in GLN, then it will preserve the dimension. So that acts on the Grassmannian. And inside the GLN action is a smaller action, which is the diagonal torus. And that acts on the k by n matrix by scaling the columns by a non-zero scalar. What happens is if I have a matrix, all of whose maximal minors are non-vanishing, and I scale the columns by non-zero scalars, then it still has this property that all the minors are still non-vanishing. So this torus action preserves this uniform matrix stratum, and so we can take the quotient, and this quotient can be identified, and I believe the name of this is the Gelfand-McPherson correspondence with the particular configuration space. So my notation for configuration space is conf kn. So configuration space is the classifies collections of n points inside a projective space. So there's a shift by one in the indexing. So I take a projective space and I take n points in it, and these n points have to be distinct. So I take distinct points, and then I consider this up to projective transformation. So two configurations at the same point in conf kn if they're related by PGLK. Okay, so inside this configuration space is a subspace of generic configurations. So these configurations are already slightly generic in that the points are distinct. But in addition, I don't want 3 of them to lie on a line or something like this. So a generic configuration is a point configuration so that the affine span of a collection of points is as big as possible, is what you would expect if they're generic. So that's this configuration space. And this Gelfand-McPherson correspondence says that the configuration space is isomorphic to this torus quotient of this matrix stratum. And the way you think about it is if you give me a k by n matrix, and you give the column some names, the columns are non-zero if you belong to a uniform matrix stratum. So they represent a point in projective space. So this gives me, each of these guys gives me a point inside P k minus 1. But of course, if I scale a column by a non-zero scalar, that represents the same point in projective space. So I take my k by n matrix, I read the points, and I read the columns, I read the columns, and this gives me n points in projective space. But I still have row operations, and the row operations corresponds to projective transformations of the ambient projective space. So if I do an overall GLK transformation, then that will just change coordinates on pk minus 1, and they'll give me the same point. Okay, so this is just explaining what this thing is, which is not I mean, it's very important, but not a particularly hard statement. And the definition of the Chow quotient, which I'm not quite going to define it. So the definition of the Chow quotient is defined as the closure of this configuration space in a Chow variety, which is a classifying space for algebraic cycles of a particular degree. So this is a little bit technical. Let me just say that the Chow quotient, Ch Kn, is a compactification of this generic configuration space. A typical point, one way to think about a point in this Chow quotient is that it's a broken toric variety. How are we supposed to think about it like this? So if you give me a point, inside here, I can take a point inside the Grassmannian that represents the point in the quotient, and I look at its torus orbit. So this, as a set, this is just in bijection with torus orbits on this uniform matrix stratum. But instead of the torus orbit, I can take the torus orbit closure, which is a toric variety. So the points inside this space are toric varieties, but the torus orbit closures of particular points with uniform matroid. And what happens is that a point in this compactification corresponds to a degeneration of this toric variety, where the toric variety breaks up into a union of sort of smaller toric varieties. I mean, I say smaller, but actually these toric varieties have the same dimension, but they have smaller moment polytopes. Okay, and so to try to draw a picture of what happens at the boundary of this Chow quotient, I mean, hopefully I'll get around to doing some examples at the end, but the kind of pictures that you get look like this. So instead of having 5 points, so a generic point inside this Chow quotient would be 5 points on P1, because I'm taking Ch2, 5. So Ch2, 5, 2 minus 1 is 1. So this is 5 points in P1. But when I work in the compactification, what happens is that you end up getting pictures that look like this, which sometimes we call stable curves, stable rational curves, where there are sort of two P1s. There's a P1 where points 1 and 2 live in, and 3, 4, and in this P1, 3, 4, and 5 are squished to a point. And there's another P1 where 3, 4, 5 and live in, and 1 and 2 are squished to the fourth point. And they have to agree in some way. Okay, so anyway, this is just a cartoon for what this Chow quotient looks like. Now, Kapranov defined the Chow quotient of the Grassmannian, and it was further studied by Q and Tevelev and Laforgue, and they realized that the combinatorics of the Chow quotient is related to decompositions of the hypersimplex into matroid polytopes. So the hypersimplex is the polytope which is the convex hull of n choose k vectors. N choose k vectors, which are the n choose k vectors, which are 0, 1 vectors with k1s and n minus k zeros. So some notation will appear later for this. But anyway, the combinatorics of this Chow quotient is hard, partly because, first of all, matroids are hard. We already have trouble sort of knowing what matroids are realizable and what are not. But in addition, we're supposed to look at how to decompose a polytope into matroid polytopes. And furthermore, there are multiple issues. So the matroids that appear should be realizable. And the decomposition should be a regular subdivision. And even if it satisfies those conditions, that doesn't necessarily mean it's realizable as a Chow stratum. Okay. So one reason to study this particular subspace is that we think that the combinatorics should be tractable instead of intractable. Instead of matroids, we will look at positroids, which are a class of matroids, which, as I said before, positroids are a class of matroids which have been classified and is in bijection with a lot of other combinatorial gadgets. So there's some hope that we can combinatorially understand this part of the Chow quotient. Okay, so Sarah, I think I answered your question, right? Yes, okay. Okay, so here's the definition and the main theorem. So the definition is the Grassmannian contains as a subspace the positive part, and this positive part is contained inside the uniform matroid stratum. And so we just look at its image inside the Chow quotient and take its closure. And that's the definition of the space. It's perhaps, the way I formulated it is a little bit unsatisfactory in the sense that in the other two cases, in the case of matrices and the Grassmannian, I defined it by some inequality. So the first case I said, take an n by n matrix and ask for the determinant to be, all the minus to be non-negative. And in the Grassmannian case, I take a k by n matrix and ask for all the maximum minus to be non-negative. In this case, I'm doing something that's a little bit different. I want to take a closure of something. And one reason it's harder to, there is in some sense a way to give a sort of inequality description of it, but it's harder because of the thing that I said in the beginning, which is that this is less like a matrix. A point in here is not a matrix, so you can't say, oh, collect all the minors and do something. Okay, anyway, the two theorems are, this guy is a polytope, so it's homeomorphic to a polytope, and it has a stratification, which so that the faces are in bijection with the faces of the polytope, and is homeomorphic as a stratified space. And then the second theorem is that there's a number of different ways to index these positive Chow cells. So the faces of this polytope are called positive Chow cells, and here are the sort of the jargon for three ways to label them. One is you can label them by regular subdivisions of the hypersimplex into positroid polytopes. I studied positroid polytopes with Alex Kosnikov. There's other recent work on this point of view. Nick Early and Lukowski, Parisi, and Williams have also studied, and others as well have also studied subdivisions of the hypersimplex into positroid polytopes. And the way we think about this is, if I take a generic torus orbit closure in the Grassmannian, then the moment map image of that toric variety is the hypersimplex. So this is this. So n choose k vertices is really big. And when I take sort of these boundary strata of this Chow quotient, it corresponds to a broken toric variety. The broken toric variety, each toric variety has its own moment polytope, and these moment polytopes are glued together to fill up the hypersimplex. So each positroid polytope in this subdivision of the hypersimplex gives me a toric variety with that polytope, and that's and these toric varieties sort of are points in the Chow quotient. Another way to describe it is as cones in something called the positive tropical Grassmannian. So I have the next slide will sort of give an explanation of this. And the tropical Grassmannian was introduced by Spy and Stumfels, and the positive part, so positive tropical Grassmannian studied by Spy and Williams. And the third description of this is cones sort of in bijection. So these three sets are in bijection, A, B, and well, the four sets, positive Chow cells A, B, and C are in bijection, and C are cones in something called the positive Dressian. I believe this was first studied by Speyer, though the name Dressian first appears in this paper of Herman, Jensen, Jostwig, and Stumfels. Okay, so let me sort of very kind of briefly explain how to go between these four things, and this is going to be a little bit sketchy, so it's like sort of half by example, so the definition of this chur k n greater than or equal to 0 is the closure of this the image of the positive part. So what I'm going to do is I'm going to take a path. I'm going to take a little path gamma of t. Epsilon is supposed to be a positive real number. There's a little path into the positive Grassmannian. So it goes into the totally positive part of the Grassmannian. And therefore, it gives me a little path. It gives me a little path in kind of the interior of this space. And then the limit, so this x here is just the limit as t goes to 0 of gamma of t, where I take this limit inside the Chow quotient. So okay, so given a point in the Chow quotient, I can find a little sort of curve that represents it, and I can ensure that this curve is a formal curve, meaning that what this means is that if I take, so gamma of t, for any t, gamma of t is a point in the Grassmannian, it has Plücke coordinates. So if I look at the Plücke coordinate of gamma of t, this thing is a function of, so for any Plücke coordinate delta I, this thing is a function of t, and let's assume, I mean, we can work with Pursue series, but let's assume it's a formal power series. If it's a formal power series, I can take its valuation, which is the first, it's the minimal degree. So let me write this out. So if if you have P of t is equal to 2t to the 5 plus 3t to the 6 minus 4t to the 8, dot, 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 dot. So if you've got a power series like this, then the valuation is 5. It's the first non-vanishing degree. So for the n choose k Plucker coordinates, I will remember p sub I. I remember the valuation of the Plucker coordinate, which is some integer. Well, if we work with pursuit series, it will be some rational. It'll be a rational number. And this is a definition, sort of at least a sketch of a definition of the positive tropical Grassmannian. Now these p sub i's are they're not just n choose k arbitrary numbers. The deltas, these Plucker coordinates, satisfy some relations, and therefore the p sub I satisfies some relations. And the simplest kind of relation is if you give me a three-term Plucker relation. So this is an identity, a quadratic identity satisfied by the minors of a 2x4 matrix. If you take this identity and you ask what happens to it with some condition of positivity, then you will get the following. Equality between the valuations, and this is called the three-term positive tropical Plucker relation, and the positive part comes from the fact that I insist that the gamma of t lands inside this positive Grassmannian, which means that the Plucker coordinates are positive, and they're positive for all epsilon. So that means that for very small epsilon, what that says is that the first coefficient of the Plucker coordinate has to be positive, and as a consequence, you'll get this kind of relation, just by extending the power series out. Points that if you have a collection of points p sub I, a collection of integers p sub I that satisfy the analog of this relation, then these things live in this positive Dressian. Notation is dr kn greater than 0. And then how do we go to the last object? To get a regular subdivision of the hypersimplex, what you do is it's a regular subdivision. So you take the vertices of the hypersimplex and you lift them up to one higher dimension, and you sort of project the lower faces. So your lower convex held down again. And what you do is you take E sub I. So E sub I is the, I said I should have written it down earlier. E sub I, for a k element subset I, E sub I is this sum of basis vectors. So that's a vertex of the hypersimplex, and the n choose k vertices. I take these n choose k vertices and I lift them up to the height EI, so they're lifted to the height PI. So this is the height that this PI is the height that you lifted. Now, you can take arbitrary PI and lift it, and you'll get a polytope subdivision of the hypersimplex. If you take the PI and they satisfy the tropical Plucker relations and you lift them, then the subdivision will be into matroid polytopes. And if they satisfy the slightly stronger thing, which is this positive tropical Plucker relation, and you lift them up, then they'll give a subdivision of the hypersimplex into positroid polytopes. Okay, so I think I have like 2 minutes left. So so that explains the main theorem. So I feel like I should well, in the last minute, say what got me interested in this, which is conversations with my physics colleagues. So the physical motivation for this is a scattering amplitude in super Yang-Mills theory. It's a function that depends on sort of some momentum vector. So here I've drawn sort of 4 particles colliding, and they have some momentum vectors. These are 4 vectors. These are vectors in 4 space. And the amplitude is some sort of probability the sort of mod squared of it is some kind of probability density. So so it's some function that depends on these momentum vectors. And in this super Yang-Mills theory, this function turns out basically to be a function on the Grassmannian mod T in a rational sense, meaning that it's got some singularities. And there's some nice linear algebra called twistors explaining it. And our hope, which we sort of did some really beginnings of it, was that in this sort of companion physics paper, is that the hope is the combinatorics of this Chow quotient, this positive Chow quotient, controls the singularities of this function. And there's some evidence for it in sort of the case of rational function in this tree case, which is sort of this function has a perturbative expansion, and the first piece of this expansion is a rational function. And in this case, there's sort of a lot of influential works, influential and kind of recent works saying that the sort of total non-negativity controls sort of singularity pose of this rational function. And somehow we're interested in this much more analytically complicated function, which has lots of integrals inside it. And we're hoping that this piece of it controls that. Okay, thank you.
Thank you very much, Tom, for a very interesting talk. So now let's see if we have some questions. You can either write in the chat, or you can raise your little Zoom hand, and I'll see. So the first to raise his hand is Sam Hopkins.
Hi
Please,
there.
Sam.
Yeah, so you mentioned that the combinatorics of the Chow quotient is very hard, and I was wondering if, in the way that matroids are kind of a combinatorial abstraction of the points of the Grassmannian, like matrices, is there even a candidate definition of a combinatorial abstraction of a point of the Chow quotient of the Grassmannian?
You mean a matroid? So there are many points in the Grassmannian with the same matroid. So the thing that is an analog of a matroid is one of these things. So if you stratify the Grassmannian by matroids, it's rather complicated stratification. The analog of that stratification is the second theorem.
But that's the positive case in the sort of like.
In the other case, we know that in the whole Chow quotient, it corresponds to regular subdivisions of the hypersimplex into matroid polytopes, but not all of them. So some of them. So first of all, the matroids have to be realizable, but there are additional constraints, and it sort of another kind of realizability is a decomposition that's realizable as well.
Okay, thank you. The second question is from JP Labbé.
Okay,
Yes.
so the question is, does it give, about the first theorem, does it give a geometric realization of the stratification as a polytope, or it gives only a statement about the topology that is a ball? It gives a geometric convex realization. In fact, the proof of theorem 1, the proof of the first theorem, gives a lattice polytope with explicit integer coordinates, which is diffeomorphic to this. Homeomorphic to this as a stratified space. Yeah. So there is an explicit polytope PKN that we can at least give you an algorithm to. We can give you an algorithm to compute a polytope which has the same phase structure as this guy. Does that answer the question? Or
I think so.
and I see in the chat that there's another question. Do you think there could be some sort of Playbig graph analog in this setting? It depends how we stretch the word analog. The proof. Okay, so let me go back to this cartoon up here. So this this point in the Chow quotient is the data of this point is actually 2 points in a positive Grassmannian mod T. So it's sort of, there's two parts to it. There's this part, which is just a configuration of points sort of in P1, and there's this there's this part. So there is a playback graph that represents this part, and another playback graph that represents that part. And so this Chow quotient for 2,5 is a very classically well-studied thing. It's called the Lin-Mumford compactification of the moduli space of curves. And in this case, one feature is that once I know which Chow cell, once I know which positive Chow cell I'm in, basically I can independently give you different playback graphs. So I give you a point in the positive Grassmannian of the correct positroid cell and another one of a different positroid cell, and I give you the collection of them once I know which stratum, and that will give me a point in this Ch 2,5 greater than or equal to 0. Unfortunately, I also drew a picture over here of something that's a little bit higher. So this is Ch Kn. So this is not as classically studied as these moduli spaces of curves. This guy, this guy is represented by a point in the total non-negative Grassmannian, and so is this guy. But to be allowed to be glued together, it turns out that there's a relation. So I can't just independently pick. I can't independently pick an arbitrary configuration with this combinatorics and an arbitrary configuration with this combinatorics and get a point in the Chow quotient. The fact that they glue to a point is some additional relation. And at the moment, I don't know a good way to write all these relations. So I can find a playback graph for this guy. I can find a playback graph for this guy, but it's not any two playback graphs with this combinatorics.
Okay, thank you. So we have two more questions. First from Ömer Gurdugan.
Hi. So at the end you mentioned that a goal is to understand the singularities of scattering amplitudes. And
yes.
As far as we can tell, this works for the singularities that are rational functions of the Pluckers. However, the tropical Grassmannian 4,8, for example, doesn't predict enough singularities for the algebraic singularities. It predicts 4, 2 seem to be relevant, but some amplitudes that should be described by this have 18 singularities. So does this Chow coefficient say more about this, or are we still looking for more letters? Because you need the cluster algebra seems to know this about these algebraic singularities.
Right. Yeah. So the thing that got us excited, and made us write this other physics paper is that we had a way to and others as well to use this positive tropical Grassmannian to explain some symbol entries in the amplitude, which were not rational functions but were algebraic functions, So the answer to your question is I don't know, because this is first of all very speculative, and even the hint that we found, we don't know how to exactly generalize that. But I am hopeful that this of two things, which is, one is that the combinatorics of this guy is tractable because everything has a positivity condition, and in addition that this combinatorics captures at least some part of the singularity behavior. So how much of it, I don't know.
Okay, thank you, Thomas. We have time for one last question from Sarah Billy.
So I'm trying to get a feeling for the Chow cells, but what is the analog of the Chow cells in the Grassmannian? I don't know that concept.
Just a matroid, a matroid stratum, or positroid cell. So, yeah.
Okay, thank you. Now it's 7:15 here in Stockholm, so that means we're done with the talks for today. Thank you very much again, Tom.
Thank you. Thank you, everyone.